Okay, in this video, I want to discuss this question. This is a proof question, so I'll show how to think about proving proof like this, logical steps that you can follow to prove something like this. So it says prove that every subgroup of a cyclic group is cyclic. So we already know what a group is, no? So you also need to know what a cyclic group is. So just to review, a cyclic group is something like, let's say G is a group. If I have to call that a cyclic group, then all the elements in that group, like group is a set and an operation on the elements in the set. So all these elements in the group should be generated by should be able to be generated by one of the elements of the group. So that's when we call a group cyclic. So for example, this set, right? So G is equal to 1 negative 1 I negative I with the operation multiplication is cyclic because if you take I can generate everything in this group. Like I to the power of 1 is I itself. Then I squared is negative 1, which means I'm doing I times I. I cube is negative I because I'm doing I times I times I. I to the power 4 is 1. So in this group, all the elements like I minus 1 minus I 1 are all generated by this single different powers of the same element I. So that's when you can call a group a cyclic group, right? So here we are saying that we are asked to prove the subgroup of a cyclic group is also cyclic. So we have to so subgroup means if I denote it by H, it will be a subset of this set, a subset of that set, and then this will have the same operation. So if I take a subgroup, uh, we have to prove that that's also cyclic, which means there will be one element in H which will be able to generate all the other elements in the set, right? So, how we can prove this is like first, since we know that G is cyclic, we can assume that that element which generates all the other elements in that group, we call it a generator, and let G be the generator of the group G. Then I'll denote it like this. So this means G is a cyclic group which is generated by this element G. Uh, I mean all the elements in G are generated by this element G. Okay. Now, so if that's the case, then if I take H as subgroup of G is a subset, right? So all the elements in H will also be some power of G, right? Uh, so let's say, so I'll take it as G to the power M, right? So what I'm saying here is uh, G to the power M is some power of G, and I'm trying to prove that all the other elements in H are generated by G to the power M, right? So, uh, so to make it more clear, right? So the elements of the group G are of this form, right? G will be there, and then we'll have G squared, then we'll have G cubed, then we have G to the power 4. So all the elements in G will be different powers of G, but the lowest power will be the generator itself, like G to the power 1 is the lowest one. So when I take a subgroup H of G, it will be some power of G, right? I mean, all the elements in H will be some power of G. For example, like let's say if there are G to the power 5, then if I had taken only these three elements, right, then uh, G cube, G to the power 4, G to the power 4, 5 are all again powers of G. So here I'm assuming that M is the smallest positive integer, such that G to the power M is an element of H, right? So now what we have to prove is everything else in H is a power of G to the power M, or G to the power M is a generator of H. So if we can do that, then we are done with the proof. So let's say let's take an arbitrary element in H, right? So some other element in H other than G to the power M, and let's call it G to the power K. So now, for to continue with the proof, you also need to know Euclid's division lemma, which says you can express any positive integer, right, as the product of the divisor in times quotient plus remainder, right? So this k, I'm saying, is can be expressed as some m times q plus r. So this m is the same as this m, right? So if this r is not there, then we are done with the proof, because then like if I replace g to the power, if I replace the exponent k with nq plus r, right, then it will look like this: g to the power k is g to the power mq plus r, right? So what we are trying to prove is that g to the power k is just is some power of g to the power n, right? So what we don't need here is this r, right? So now, according to Euclid's division lemma, when you write something like this, you have this condition that 0 is less than or equal to r is less than m, right? That's because if r is equal to m, uh, right, then we don't need we don't have a remainder, right? Because if this term says uh, q goes like m goes q times into k, right? So if you want example for that, I can write like 13 is I can write that as 2 times 6 plus 1, right? So this r has to be less than 2, right? And it can be 0 or it can be any integer that is less than uh, 2, right? So mm, okay, let me okay, now our goal is to, okay, I can rewrite this as like this. I can rewrite this as g to the power m to the power q times t to the power r. So that's g raised to k. So what are we trying to prove? We are trying to prove that g raised to k is some power of g raised to m. Because if I can do that, then I'm saying any arbitrary element of h is a power of g raised to m, which means g raised to m is a generator of that root, and so I can conclude that it is cyclic. Now the problem here is we don't need this, right? So now g raised to k, this is already We have assumed that we have taken g raised to k from H, so which means g raised to k is an element of H, right? Now, what about this one, right? G raised to m is a generator of, or yeah, g raised to m is the generator of, or is in H, right? That's what we have assumed. G raised to m is in H. So when I say g raised to m to the power of q, which means I'm multiplying g raised to uh, the g raised to m with itself like q times. So according to the properties of the group, if you multiply an element of the group with itself many times, you still end up in the same group, right? So which means this is also an element of H, right? Now is can I say that g raised to r is an element of H? Now if I just take this to this side, right? So it'll I can write this as g raised to k times g raised to mq inverse is equal to g to the power r. Now we know that g raised to mq, this is in H, right? So its inverse should also be in H because that's a property of the group. Now g raised to k is in H, this is in H, so the product should again be in H because that's again has to satisfy the closure property of the group. Now which is equal to g to the power r, which means g to the power r is also in H, right? Okay, so if g to the power has to be in H, right? If g to the power r has to be in H and g to the power m is in H, where m is the smallest positive integer, r has to be less than m, right? r has to be less than r has to be less than m, and it is m is the smallest positive integer, which means r then can only be 0, right? Because if r is anything else, then m is not the smallest positive integer, it is r, right? So hence we can conclude that r is 0. So if r is 0, this term becomes 1, and now we can write g to the power k as g to the power m to the power q, which means we have proved that any arbitrary element which I took from the subgroup H is a power of the element g to the power m in H, where m is the smallest positive integer, which means H is also cyclic. So that's the proof for that question.